This is NEAF Talks. And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Welcome back, everyone. Are you having a great time here at NEAF today? It's a really good, we had some really, the first couple of speakers were outstanding. Our next speaker is from Lockheed Martin. He has worked on some very high-tech, sophisticated satellites. He's the Vice President of Program Development, and we are very honored to have with us today from Denver, TIM GASPERRINI. Please welcome Tim to NEAF 2018.
Thank you. Thanks. Great to be here. It's great to be here. Thank you very much. I'm going to talk about 4 missions, one of which is getting ready to launch in the next couple of weeks, and the other 3 have launched and are sending back data from orbit. So it's a pleasure to be here. Lockheed Martin has a long history of building planetary spacecraft and sending them to various places in the solar system. I'm going to talk about 3 planetary spacecraft and 1 Earth-observing satellite that we've built. I'm going to talk about Juno, I'm going to talk about InSight, and I'm going to talk about OSIRIS-Rex, and then we'll finish up coming back to Earth and talk about the GOES-R satellite and some of the, not the weather aspects of the GOES-R satellite, but some of the other aspects of GOES-R. So we'll start with the InSight Mars lander, which is right now sitting in Vandenberg, waiting to be launched on an Atlas V, actually 2 weeks from Saturday. So why InSight? You know, all of the terrestrial planets, they share some common aspects to them. They all have a core, they have a mantle, and they have this similar formation. We've got pretty good data for two of those planets, Earth, and also we've got some data from the moon from having visited the moon. And so we're going to Mars because we can. Mars, even though it was formed a while ago, the imprintation of the evolution of Mars has not yet destroyed some of the evidence, like some of the evidence is destroyed on the Earth through all the volcanism and evolution. Okay, so the purpose of InSight is to go and learn about the formation of terrestrial planets. Even though we're going to Mars and we're going to learn a lot of things about Mars, it's about learning about the formation of terrestrial planets through seismology, through geodesy, and then through heat flow. So the instruments on InSight, there's a number of instruments that the lander will bring to the surface of Mars. The first one is a seismometer, which will measure, is an incredibly sensitive seismometer. It can measure the effects of the wind on the surface. It can also measure the impacts on the surface, and it can also measure any of the volcanism that takes place. In fact, it's so sensitive that it can measure deflections in the planet of close to the size of a hydrogen atom. And so we have to take some very special precautions to actually protect the seismometer and measure the environment around the seismometer so that that information can be removed from the measurements that are taking place. We also have what we call is the HP3 instrument, which is a heat flow probe, and it takes what we call the mole and burrows down 5 meters into the surface of the planet, and the connection between the mole and the spacecraft has temperature sensors, and it has heat sources, so that we can send out pulses of heat. We can measure the response of the rock face or the surface of the planet there, and we can understand what the heat flow properties of Mars are. And this is a little video of the mole of how it works. So we basically position the mole on the surface, and it will hammer itself down 5 meters into the ground. It's a fairly, when you look at it, it's a fairly elegant device that they have built. And I'll talk a little bit about the timing of how long some of that takes. The third, let's see, there we go. The third instrument that we have is actually not an instrument at all, but it's using the communication system on the satellite. What we do is we measure Doppler response of the satellite relative to the Earth. So we'll measure the motion of the location of the satellite relative to the Earth to within a couple of centimeters. And what that will tell us is that will tell us how the planet wobbles as it's going around in its orbit and in its rotation. And we can use that to determine the content and mass of Mars and help us to understand what the interior structure of Mars looks like. And the way that this works is we'll get to Mars and we will deploy the seismometer on the surface of Mars, and we'll release the cabling so that it's not flapping in the wind. We'll come back and there's a wind cover, a wind shield that actually goes over the seismometer to protect the seismometer from the wind. We'll come back, we'll pick up the HP3 or the heat probe, and we will put that down on the surface, and then it will start hammering down into Mars. Okay. From a mission overview, the principal investigator is Bruce Bannert at the Jet Propulsion Laboratory, and they are also responsible for running the mission. Lockheed Martin builds the satellite, and we do mission operations up until the time that we get to Mars, and then the Science Operations Center takes over those. The seismometer is built by CNES, the French space agency. The heat probe is built by the Germans. So this is an international program that we're doing. Sort of a mission overview. As I said, we'll launch in 2 weeks. And then in the September timeframe, or excuse me, November, we will get to Mars. And the cruise duration depends on when we launch. It's a fixed arrival date at Mars, so we get there in November, no matter when we launch. And so it's about 170 to 200 days of travel. And our entry velocity when we get there is about 5.6 kilometers per second, about 12,500 miles an hour. So we slow ourselves down from 12,000 miles an hour to 0. And there's basically 4 ways that you can take out energy when you get to Mars. You can use a heat shield, which we do. You can use a parachute, which we do. You can use engine thrust. So we will do all 3 of those to get ourselves down to the surface of Mars. The 4th way is actually use the planet to stop yourself, and we try and do that very sparingly. And so the legs actually on the lander have energy absorption devices. So the last little bit of energy is taken out by the legs as we land on the surface of Mars. So the other interesting thing about InSight is that this will be the first mission where we have ever taken CubeSats to a non-Earth body, or put them not in Earth orbit. And so JPL is developing these CubeSats called MARCO. And normally, when we come into the surface, when we come into Mars for entry, descent, and landing, the orbiters that are at Mars, either Mars Reconnaissance Orbiter or Mars Odyssey, will collect the data and relay it back. The Mars Reconnaissance Orbiter does not have the capability to bent pipe the data back to Mars, so we collect it and then replay it. And so you have to wait an hour or so to find out if you actually were successful at landing, which is a little nail-biting. So the purpose of the MARCO is the MARCO CubeSats are going to go to Mars, and they're going to relay the data from the lander as we come in, and then send it back to the Earth, so we'll have near real-time, one-way light time data for Mars entry. So it's pretty exciting. There's a lot of technical challenges associated with these CubeSats for turning them into sort of traveling between the planets, if you will. But we're hopefully, and everybody's excited and hopeful that their work. They're an experiment that is not part of the InSight mission, but is launching with the InSight mission. This is where InSight's going to land. It's going to land very close to Opportunity. InSight is based off of the Phoenix lander. Phoenix landed way, way, way up above the Arctic Circle of Mars. And that mission was life limited from the beginning because it's a solar-powered lander, and the sun went down on it. So InSight, being at the equator, will not have that problem. It will have full sun for the entire Martian year. What will limit its life is the dust that will accumulate on the surface of the solar rays. The mission itself takes, the first couple of months are taken for getting the lander stabilized, finding a site to deploy those instruments, because when you land, there may or may not be small rocks that we have to avoid. And then depositing those instruments. It takes a while at 15 or 20 minute light time. Every time you want to send a command and get confirmation back, it's like an hour-ish to do that. And we don't have full continuous 24/7 communications, so it takes a while to actually get the instruments deployed. So first the seismometer will deploy, then the seismometer cover will deploy, and then the HP3 will deploy. And then you saw that HP3, it's like click, 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 click. And it's got to go 5 meters, so it's going to take weeks for it to gradually snake itself into the ground. So the overall mission, we're 3 months on the surface of Mars-ish before we even are into the prime science mission. This is what the spacecraft in itself looks like. You see that cartoon-looking picture shows the different portions of the spacecraft. There's a cruise stage, which is what is used to get the InSight to Mars, and it separates. There's a back shell and a heat shield, which protects it as we're coming into the atmosphere. And then the lander's nestled up inside of it like a little Russian doll. And we go through a series of transformations as we come into the planet. So you can see up in the upper left-hand corner is what the heat shield and back shell actually look like. And then down in that sort of middle picture is the lander as it was deployed in the clean room out in Denver. So I'm going to change gears here and talk about OSIRIS-Rex, which is going out to an asteroid. And I don't know how many of you were here for Kirsten's talk, but she talked about the asteroid Bennu. And OSIRIS-Rex is actually going out to Bennu and to collect some information on that asteroid. So why OSIRIS-Rex? As we have looked out into the heavens, we've seen organics as we look out there. And as you know, the Earth was bombarded in its early days of formation. So it's a reasonable assumption that some of the organics that showed up on the Earth came from off of our planet. Okay? Carbonaceous chondrites are meteor types that we already know have carbon and some functions of amino acids. If you think about how our solar system is organized, you have the Kuiper belt sort of way out there beyond the orbit of Pluto, and you've got the asteroids between Mars and Jupiter. And so in those bodies or in those populations, there are asteroids that are carbonaceous and have organics. And so if you kind of go through the math, there's hundreds of thousands of these bodies out there, some of which we know about, some of which we don't. When the OSIRIS-Rex mission was being proposed, there was about known 7,000-ish kind of near-Earth, what we call near-Earth asteroids. Those are the ones that are not necessarily stay in the asteroid belt itself, but actually come close to the planet. Okay? Of those, there's 192 that we can easily get to. Some of those 7,000 are very difficult and take a lot of energy to get to. There's a couple hundred that were easy to get to. There was 26 that have a diameter big enough that once we get out there, we can actually maneuver around them. Something bigger than a couple hundred meters. Okay. Of those 26, there's 5 that are carbonaceous. And so from that population of 5, if you think about it, we started with 500,000, or over 500,000, and got down to 5. And Dante, the principal investigator, selected the asteroid Bennu. And so we're going out to Bennu to collect some samples. Okay. Now, why Bennu? Bennu has been a very characterized asteroid. We know its size. We know what its orbit looks like. We understand what its albedo looks like. We understand its rotation rate to the best of our ability from Earth-borne measurement systems. Okay. The mission itself has sort of five different aspects. One is origin, in that we're going to go to Bennu and we're going to collect a sample, a pristine sample of the asteroid, and we're going to return it to Earth. Okay. The other reason is for both spectral and resource interpretation. Even though we're able to see these things from the Earth and we're able to ascertain what we believe the composition is, we have no ground truth data to back up those interpretations of the measurements we've been able to take. So we'll take a series of instruments to Bennu and make spectral measurements of the asteroid, which we can then corroborate the spectral measurements on the Earth. Okay. The fourth reason is for security. And any of you that were in the audience for Kirsten's talk, where she talked about asteroids and their possibility of hitting the Earth, Bennu is 500 meters in diameter, give or take. And it also has an orbit that brings it very close to the surface, to the Earth, in about 110 years. And so we're going out to study something called the Yarkovsky effect. And I've got a snippy little video here, a cute little video that explains sort of what the Yarkovsky
Just
effect.
like the Earth, asteroids are spinning as they orbit the Sun, so they have a day and night cycle too. Because of this rotation, the warmest part of an asteroid isn't the spot right in line with the Sun, it's slightly to the side. As the photons radiate from this warm spot, they give the asteroid a little kick, similar to the recoil force on a firing cannon. This recoil force can slow an asteroid down or speed it up, like a car when the driver pushes the gas or brake pedals. If the asteroid is spinning such that the warmest spot is slightly in front, the recoil force will be backwards, and the asteroid will slow down a bit, like a car hitting the brakes. But if the asteroid is spinning the other way, the warmest spot will be slightly behind, and the recoil force will give the asteroid a push forward in its orbit, like a car hitting the gas.
All right. So Yarkovsky effect, basically everything in the solar system absorbs energy from the sun, and it also radiates photons from the sun. And so the Yarkovsky effect, as it was illustrated in the video, can change the orbit of an asteroid. You think about, for Kirsten was talking about nuclear bursts and moving an asteroid with nuclear bursts, okay? But over long, incredibly long periods of time, photons count. And so they will change the orbit of celestial bodies as they go around. And especially, for the Earth, it doesn't really matter a whole lot. For something small, it matters far more than it does for the Earth. And so we're going out to measure the Yarkovsky effect to try and understand how that influences or could influence the orbit of Bennu. And then the last reason we're going out there is to explore the regolith, to understand at our landing site, to take spectral data at our landing site and understand what both optically and spectrally our landing site looks like, so we can put the samples that we bring back in context. Dante Loretta is the principal investigator. He's at the University of Arizona. This mission is run out of Goddard Space Flight Center. We build the satellite and do the mission operations for it. And then there's a various series of instrument providers, some NASA centers, some universities for the OSIRIS-Rex mission. So this is what the spacecraft looks like. This was when we were getting ready to go into the thermal vacuum chamber. We're all dressed up with our thermal blankets on and in a nearly flight configuration. And so let me point out to you here where the instruments look like. So there's a set of cameras that we have there's, that are on the top deck of the instrument, the polycam and the map cam. The polycam will measure or take pictures of the asteroid, and then the map cam is used for mapping. What they call the SAM cam is the sample camera, and I'll show you a picture from the sample camera from the satellite. What that's for is once we put the sample into the return vehicle, we're going to take a picture of it to make sure that everything looks right before we close up the return vehicle. Okay. There's also 3 spectrometers, 2 in the infrared. We go from about 0.4 microns up to 50 microns between those two infrared spectrometers. And then there's an X-ray spectrometer that is also looking at the asteroid. We also have a gravity measurement similar to the RISE instrument on InSight. We take gravitational measurements of the asteroid as well. And we have a sampling system. We've got a sampling arm, and I'll show you some pictures of the sampling arm, and then a sample capsule that we will bring back to Earth, and it will enter the Earth's atmosphere and be returned out to Utah, similar to the way that we returned a sample on STARDUST. So the sampling period, we'll get to the asteroid, we'll approach the asteroid here in August, and then there's about a year-long period where we're characterizing the asteroid. We're looking at the sample sites, looking for places that are safe to land, that are what appear to be scientifically interesting from either the spectrographic data or the optical data, so that we can then create a sample, okay? And once we decide we're going to take a sample, we'll neck down a whole series of activities over the year to get us down to a single sample site. What will happen is we'll separate the sampler device. Now this is a sample head on the end of a robotic arm. And so that sampler arm will deploy. The robotic arm will get it into position. The sampler head will get to its position. It will come down. And think of this as a reverse vacuum cleaner. So since there's no vacuum in space, we bring our own gas with us. And we hit the asteroid for about 3 seconds, release a gas blast, which will then what do you want to say? Put the regolith into that gas pattern, and it will put it in the sampler. We will then put it inside of the sample return capsule and close it up. One of the interesting things that we do is we have to bring back, our requirements are we got to bring back at least 60 grams of an asteroid. And you say, well, how do you measure 60 grams of an asteroid when you blast it in there? Well, the arm is long enough that what we'll do is after we take a sample, we'll extend the arm and we'll spin the satellite. And we can, from the moment of inertia change on the satellite, because of the sample out there, determine how much sample we have. So we'll do it before when the thing's empty. We'll do it after when we have a sample. And if we don't have enough, we go back. We have enough time, enough gas, bring enough gas with us to do it 3 times. So. These are some pictures. We flew by the Earth, and you can see the picture of the Earth and the picture of the Sun. And that's the picture of the sample return capsule as it's sitting on the deck from the sample camera. So what happens is that white part will open up like a clamshell relative to the brownish part, and you'll be able to see the sample when it's installed. Okay. I'm going to switch gears to Juno. So we're going to leave Bennu. We're going to go out to Jupiter now. And Juno is a lot like InSight in its mission objectives, okay? We're going to Jupiter to learn about Jupiter, but we're really going to Jupiter to learn about the formation of the solar system. So just as InSight was trying to understand the formation of the rocky planets, Juno is trying to look at the formation, how the gas giants impact or influence the formation of the solar system. Okay, and we have a series of instruments that are laid out on the Juno satellite. So again, there's origin. What is the origin of the solar system? We have as well the interior. We're trying to understand the interior because all we see is the gas on the surface of the planet, right? We can't see beyond that. So we're trying to understand what's the interior structure of Jupiter, understand the atmosphere, and then Jupiter has a gigantic magnetic field. And auroras that are bigger than anything else in the solar system, and we're trying to understand those as well. And each of the instruments is characterized or selected to address one or more of those scientific objectives. Scott Bolton, who is the principal investigator at SWIRI. This mission is also run by Goddard. We also build the satellite and do the mission operations from our offices in Denver. So this is what the spacecraft looks like. You can see the magnetometer is clear out on the end of the solar array. That's to get away from the influence of the magnetic field inherent with the spacecraft. All the solar arrays are magnetically compensated because as you're generating power, you're generating current, which generates magnetic fields. The solar arrays are magnetically compensated so that they are magnetically quiet, so that they don't disturb the magnetometer. And you can see the location of the various instruments around Juno. Juno is different than some of the other spacecraft we built in that it's a spinner. And we do not have reaction wheels in it, so it spins constantly. So all the instruments had to be designed to be a spinning spacecraft. That was done primarily for weight and power and a whole bunch of other reasons, because since we are a solar-powered mission at Jupiter, we take roughly 12 kilowatts of power at the Earth and cleverly turn it into 400 watts when we get to Jupiter and run the spacecraft on that. Half of it's to keep the spacecraft warm, half of it's to run those instruments. So we do a whole lot of stuff with very little when we get to the planet. Now, the interesting thing is we do have a lot of data coming back from Juno, and it's rewriting our understanding of what Jupiter looks like. The structure of the atmosphere is completely different than what they thought it was. There's cyclones up on the North Poles. I'll show you some pictures. It's just unbelievable what's going on. And as they're looking at formation theories of the solar system, they were primarily looking for water in Jupiter. And some of the early indications they're getting back for the water content of Jupiter is that it's saying that the carbon-rich model of the formation of the solar system might not be the right one. So, but if anybody's interested, there are piles of peer-reviewed papers out there with some of the detailed things that we're learning about Juno. So let me start with pictures. Some of you have probably seen these. This is the southern hemisphere of Jupiter. It looks completely different than the banded view that we have always seen of the nice bands of Jupiter. These are the pearls that are the little white storms on Jupiter in the reddish bands. You can see different images of those pearls of the Juno camera that took a picture. And I want you to think about this. The Juno cam is like a megapixel camera. Okay, I mean it's like your iPhone's not even got a megapixel camera on it, but it's returning images like this as we get there. Here's some more. These were taken at the 8th pass around Jupiter, just some different time-lapse photos of Jupiter. And then the latest pass we just did, which was about 3 or 4 weeks ago, this is all those pictures strung together. And we fly 4,000-ish kilometers above the cloud tops. And so that's right about there. You're about 4,000 kilometers above the cloud tops. And you think about how big Jupiter is and what 4,000 kilometers is relative to the diameter of Jupiter. It's pretty impressive. And so then we're coming away from the planet. So, and there's a good view of I think that would be the southern hemisphere because we come in over the north generally. Great Red Spot. These are some pictures of the Great Red Spot, and there's a little time lapse that's been put together of how that Great Red Spot moves around as we get close. These are images from Juno Cam. Now, the interesting thing about this, however, is looking at it optically, you say, yeah, we've seen the Great Red Spot, okay? But the microwave radiometer instrument on Juno has the ability to peer down hundreds of kilometers into the clouds, okay? And so this is a sort of a combined image product that has been developed. So you look at the top layer, And that's what the great red spot looks like. That's what we see. But you look at what the structure of that looks like as you go down, and by the time you get 50 kilometers down into the atmosphere, it doesn't look anything like it looks like up on the top. And this was not an expected, they did not expect this when they went to Jupiter, they did not expect these kind of results. So a lot of the investigators are a bit scratching their head on what this means and how it impacts some of the theories of Jupiter. We also have some infrared instruments, and so this is what Jupiter looks like in the infrared. And so you see those clouds that are optically colored differently. Some are red, some are gray, right? But you can also see in the infrared what Jupiter looks like. And if you look at that sort of one in the middle, you can see the great red spot as it goes around. There it is, right there. You can see the great red spot as it goes around. And you can see the string of pearls on the bottom, the little circles that go around. And so they are, so this is telling them different, they're learning all about the clouds of what those clouds are because there are different temperatures, those different bands on Jupiter. Okay. We're going to switch to the GOES satellite, and I'll give you a quick weather primer right now. There's two different types of weather satellites, okay? There's polar orbiting satellites, and there's geostationary satellites. When you whip out your smartphone and you say, hey, what's the weather going to be like tomorrow because I want to go for a bike ride or I want to do something, the vast majority of that, 70 to 80% of the data that feeds the models, that gives you that information, comes from the polar satellites, okay? But the polar satellites, that's great, but the disadvantage of the polar satellites is as they go around, their repeat rate on the surface of the Earth is very low. And so with the two satellites that we have, we get a couple of repeats over the same spot of the Earth twice a day, okay? And if you have a severe storm barreling down on the East Coast, okay, you want more constant you want to see more constant image of what's going to happen, right? Hence the geostationaries that look at the same place on the Earth 24/7 and can watch what's going to happen with that severe weather. So the polar satellites mostly feed the weather models. The geostationary models are what's used for severe weather. Okay. So the GOES satellite itself consists of a Earth orbiting satellite. NOAA builds procures the satellite. Goddard manages it. We build it. And then the instruments are provided by a number of folks. We actually, at Lockheed Martin, provide or purchase 3 of the 6 instruments on the GOES satellite. So we've got a large solar array that generates 12 kilowatts. We've got an antenna wing that we use for a lot of the data services. And then there's an X-band antenna that's used for the primary downlink at 100 megabits per second. There's 2 Earth-pointing instruments. One is called the Advanced Baseline Imager. The other is called the GLM, the Geostationary Lightning Mapper. GLM is a first-of-its-kind lightning mapper in geostationary orbit. We've never had anything like that in orbit before. There's 2 sun-pointing instruments on the solar array because the solar array looks at the sun. We've got a solar-pointing platform on the solar array that look at the sun. One Exus looks at the sun primarily in the X-ray. SUVI looks at the sun in the ultraviolet. And then there's 2 other instruments. SICE, which is a particle measurement, measures the intensity and flux of particles as they get by the spacecraft, and then a magnetometer. And I'm going to talk about how all this works relative to both space weather and how some of both the Advanced Baseline Imager and the Geostationary Lightning Mapper are also doing other things other than weather measurements. So normally, this is the kind of thing that you see coming from the Advanced Baseline Imager. So this was this summer where you saw all of those hurricanes. This was the eclipse. So occasionally we'll get to see something like this, where this was the eclipse that took place last August. So this is what the eclipse looked like from the GOES-R spacecraft. There was also an eclipse in South America that happened earlier in the year that nobody particularly cared about, apparently, because all they talked about was the one that came across the United States. And so you can see the shadow of the moon as it goes across the globe. I mean, I don't know. For me, I get excited. I see stuff like this. It's really exciting to see this kind of thing. And let me talk a little bit about the geostationary lightning mapper right now. Normally, we're looking at lightning, and you see something like this from the geostationary lightning mapper. This was a huge storm that stretched across the United States last year. You look at that lightning, okay? And then you say, okay, here's this little tiny thing right here, okay? And you say, that's nowhere near as impressive as the lightning that spans across the United States and disrupted power and disrupted people's lives, okay? Well, this does not look all that impressive from geo, okay? But if you happen to be on the ground, okay, let's see. This is what you would have seen, okay? And I don't know how many of you remember the asteroids, or the meteors, excuse me, that took place over in Michigan, okay? So what GLM has the capability to do, because it images the Earth 500 times a second in the infrared, if you have anything that's coming through the atmosphere that's warm, like lightning, or a bolide, meteor, okay, the GLM instrument will pick it up. And in fact, we've been able to see all the unclassified bolides that have come through over the disk of the Earth that we look at since the instrument was put up there. And NASA Ames has recognized the advantage of this and has taken what we call the level 2 GLM data, which is the data before, it's the raw data essentially with a little bit of manipulation on it. They've taken that raw data and they have put it into an algorithm set that goes out and looks at that stuff and detects the meteors as they come through. Because a lot of times you don't have meteors when there's lightning, you just have it, like as you saw before, it was just this bright spot out in the middle of nowhere. And so this is an exciting thing, something we never ever anticipated when we built the instrument. And in fact, the resolution, the temporal resolution, since we take pictures every 2 milliseconds in the infrared, you can get what's called the light curves for the meteor. And so this was the light curve for the meteor that came through in Michigan. And so you can see it broke up into 2 big pieces that then disintegrated as it came through the atmosphere. And so they can use this as a measure of the intensity and the energy that was in the meteor itself, or the bolide. So I'm going to switch gears to space weather. As you know, our sun just spews stuff out constantly, okay? Some of that stuff radiates out into the cosmos. Others of it comes to the Earth. And we are protected by the magnetic field of the Earth. And some of that energy comes down the field lines and creates the aurora on the planet. Other of that energy comes down and it disrupts things, okay? It disrupts satellites that are in orbit. It can disrupt communication systems. It can disrupt power lines. The most interesting one to me, as you think about it, that's energy, that's electrons that come to the Earth. They've got to go somewhere. They go through the Earth, the ground plane of the Earth. And if you've got buried electric cables, or you've got pipes, pipes are generally, the Earth is generally moist. It can cause corrosion of those. And so space weather, or the energy coming off of the sun, can cause all kinds of issues here on the Earth, okay? And if you think about our sun has a lot of different phenomena that are coming off of it. It's got light, it's got X-rays, it's got coronal mass ejections, there's solar flares, there's solar wind, there's all kinds of things that are coming off of our sun. Some of it comes to us, some of it doesn't. Okay, some of it is radiated out into space. The interesting thing is that each of those phenomena have a different temporal signature, or they take a different amount of time to get there. Light, as you know, takes roughly 8 minutes, okay? The X-rays, depending upon where they come from, might take a little bit longer, okay? The solar wind is constant, but the effects of the ejections on the sun take roughly 4 days to get to us, okay? And those things that happen directly in line with us really don't matter because we're moving, the sun's rotating. It's the stuff that happens at off angles that could be the potential problem to get to the Earth, to get to us, okay? So GOES has a series of instruments on it. Those are the solar instruments and the particle instruments to help us understand what happens. I don't know how many of you are aware, but in Boulder, Colorado, there is the Space Weather Prediction Center. And they issue, you can go out on the web, and every day they issue the space weather. They tell you what the space weather is around the planet. And so they take instruments, they take data from the GOES satellites, they take data from other satellites, meld it all together into a space weather report, if you will. So the way that this works, let me explain how all these works. So the SUVI instrument takes pictures of the sun in the ultraviolet. So basically 8 minutes from when something happens, we see it on SUVI. So SUVI detects whether there's a solar flare, coronal mass ejection, or anything that's happening, coronal hole on the surface of the sun, okay? The EXIS instrument measures the intensity or the strength of that solar flare or coronal mass ejection in the X-ray. So it's measuring how strong that is, okay? But we're still not quite sure whether that's coming right at the Earth or that's going to miss the Earth either behind us or in front of us. So NOAA has another spacecraft called the DISCOVER spacecraft. DISCOVER's purpose is to monitor the solar wind and determine from what we call the L1 pointer, about 1 million miles from the Earth towards the sun, it's determining how much of that solar wind is coming to us. And if we see it there, then we know that it's coming to the Earth, okay? Once it gets to us, the SEIS instrument will measure the amount of particles and the flow of the particles and the intensity of the particles as they get to the Earth. And then the magnetometer will measure the effect on the magnetic field. So the whole system, the GOES system and the DISCOVER system, can play together to monitor the space weather. If you look at, these are 6 images come from SUVI. The SUVI instrument has 6 different channels in the ultraviolet, okay? And those channels are tuned to specific things. There's a couple of channels that monitor solar flares. There's a couple of channels that measure active regions or coronal mass ejection. There's one that monitors coronal holes. And then there's one that monitors the solar filaments. Okay? And if you look at those pictures, every one of those pictures was taken at an identical time looking at the same sun. Okay? Just look at them for a moment, and you look at, for example, this picture, and you look at what the corona looks like in this picture versus what the corona looks like in this picture. Completely different. Okay? So with the different channels that we have, we can measure and look at different effects and phenomena on the sun. And this is just some videos, and if you look at the lower orange one, you'll see on I guess it's this side, you'll see sort of a little solar flare that comes out, right? If you look at the others, you can't hardly even see it in the other wavelengths. And so it's important that we study the sun in multiple wavelengths to understand exactly what's going on, because a single wavelength doesn't tell us enough information. Let me show you these last ones. These are some more pictures of SUVI. The one on this side, the orange one, is a large solar flare. But the one on the yellow one is the largest solar flare that has been recorded in the past dozen years. It was a Class 9 solar flare that SUVI picked up last year. I think it was in August or July. And so you just look at that, and it rings half of the sun. It's just a tremendous amount of energy that's being released from the sun. and but the SUVI instrument can see it because it's looking in multiple channels. So thank you very much. I appreciate it.